Hello and welcome to this flip learning session on projectiles. This seeks to build on two topics that we've covered recently, resolving vectors into two components and equations of motion. So let's recap the resolving vectors into two components. So if this black arrow represents a vector, we can split it up into a horizontal component and a vertical component. So if we draw on the horizontal component in red, represented there, and then we draw on the vertical component in blue, put in there, okay, we can say that these two components are equivalent to the single black arrow that we've got represented there. So altogether these three arrows represent a right angled triangle, which we can use trigonometry to work out the different values of the sides. So if I place that back over there, if we know the angle in here, then we can work out, and we also know the value of the vector that we're trying to resolve, the magnitude of that vector, we can work out the red component and the blue component, the horizontal component and the vertical component. So let's set theta as 36.9 degrees. So that's that angle in there. And we'll set the magnitude of the vector as 15 meters per second. Now, using SOHCAHTOA, we've got SOH, so therefore sine theta is equal to opposite over hypotenuse. So in this case, that means 15 sine 36.9 is the value of this side of the triangle here, okay, which is the same as the blue arrow that we have here, which is equal to 9 meters per second. Then if we do the same for the horizontal component, which is the red arrow, we've got the adjacent side to the angle, so we're going to use the cosine is adjacent over hypotenuse, so cos theta is equal to the adjacent over the hypotenuse, so that's the value of the red arrow there divided by the value of the black arrow there, and we get 15 cos 36.9 is equal to 12 meters per second. So what does this mean? Well, it means that the 15 meter per second value that we have here for our vector at 36.9 degrees above the horizontal is exactly equivalent to two vectors at right angles to each other, one horizontally with a magnitude of 12 meters per second and one vertically with a magnitude of 9 meters per second. They are the same thing. So how does this relate to projectile motion? Well, in projectile motion we've got to deal with two situations. The first situation is we have the object is going up and then coming back down. So that's its vertical motion. At the same time as it's doing that, it can be moving horizontally across the ground. So we have an object which moves through the air, something like that. But we are going to be able to deal with that situation by splitting up the motion and dealing with two problems, a vertical motion and a horizontal motion. So let's deal with our vertical motion exclusively first. If we take an object, a ball, and throw it up in the air, it will leave our hand, it will start to slow down as it goes up, it will momentarily stop and then fall back down again. Now, with this problem, we can use SUVAT because if we, on Earth, we have a constant acceleration of 9.81, or in this case, minus 9.81. So if we lay out our problem as we would normally, we've got S, U, V, A, and T. We have minus 9.81 for our acceleration, and we've also got a final velocity of 0 meters per second when the object is at the very top of its flight. What we have to be careful is that the value for t is the value for this point where it's just gone to the top. Okay, so the actual time of flight is for it to go to the top and come back down. So in other words, if we solve this problem, we need to double t to get the complete amount of time that it's in the air for. Now if we consider the horizontal motion, horizontally, the object is considered to be moving at constant speed because we're not taking into account any air resistance or drag forces. So in this case, U equals V, which equals the horizontal component that we've worked out initially in our problem where we split the component into, split the vector into its two components. The horizontal speed is a constant speed, so we just need to say for this that velocity is equal to distance over time. So this drawing represents the path taken by a projectile, and on it is drawn the vector, or the arrows representing the magnitudes of the horizontal and vertical component of its motion as it goes through this arc in the air. If you notice, all the blue arrows have exactly the same length, representing that they are not changing. The horizontal component of the velocity remains constant, so it's always travelling at the same speed horizontally. However, the arrows representing the vertical motion reduce in size, as we can see, until it becomes 0 at the absolute top of the flight, before increasing again downwards as it drops back down to Earth. The crosses on the diagram represent 1 second time intervals. So if we look at the vertical distance, if you like, between the crosses, this is trying to show that they are all equal, because the distance travelled per second will be remaining constant, because as we've said, the horizontal motion is a constant velocity. However, the distances between the crosses vertically, are reducing all the time as it either slows up or speeds up, going up or down. So what can we be asked in a projectile's problem? Well, we can be asked to work out how long the object's in the air, and also to work out how far away it will land. Right, let's go back to our original vector. We had a problem here that we looked at initially, where we had an initial velocity of 15 meters per second at 36.9 degrees above the horizontal. So let's say that then is problem. A ball has been kicked with an initial velocity of 15 meters per second above the horizontal. How long does it stay in the air, and how far away does it land? Well, the initial part of the problem would be to split the 15 meters per second vector into its horizontal and vertical components, but we've already done that. So we can see that we worked out that vertically it had an initial velocity of 9 meters per second, and horizontally it had an initial velocity of 12 meters per second. Now, the 9 meters per second can go into our SUVAT style problem, and the 12 meters per second stays as a constant velocity as it travels horizontally. So let's see how we can lay out and solve this problem, which is to use the information that's here to work out how far away it lands and how long it's in the air. So if we move this out of the way, we can split our whiteboard area, paper, whatever we're working on, into two sections, and we'll put a box in the middle there and split that up like that. So this is going to be the part where we work out our horizontal information, and this is going to be where we work out the vertical. So vertically, the information that we've got is, we don't know anything about the distance. We've got an initial velocity of 9 meters per second. We've got v of 0, and we've got an acceleration of minus 9.81 meters per second squared, and the time is what we want to find out. So we can find time from this information by using v equals u plus at, and substituting into that, we've got 0 is equal to 9 plus minus 9.81 times t, so minus 9.81 t. If we rearrange that, we have t is equal to 9 divided by 9.81, which gives us an answer of 0.92 seconds. But this value of the time here is the time that it takes to get to the top of the flight to the point at which v equals 0. So the actual time that the ball is in the air is going to be double that, so 1.84 seconds. And we're going to put that here in the box that we have. So that time is linked, so it's the same for the vertical motion as the horizontal motion. The difference being the horizontal motion takes place at a constant speed. So we can tell that the distance covered is going to be equal to the speed, velocity, times the time that it's in the air. So our horizontal velocity is 12, so we can substitute that in, and it's 12 times 1.84, which gives us a value of 22.1 meters. So the solution to our problem is the time that it's in the air is 1.84 seconds, and it lands 22.1 meters away from where it was kicked. So that's it. That's a quick introduction into projectile motion style problems and how to solve them.